Hi, what's going on, guys? So today I'm going to work through this problem, which is basically hypothesis testing combined with like confidence interval interpretation. I will work through this problem in RStudio and just show you how to do each one of the questions and also explain some concept about hypothesis testing. So first of all, I'm gonna build a new file, exercise.rmd. So this is our R Markdown file. So so first thing first, I'm going to import the data. So the first step, import data. Okay. So what I need in this exercise is I need the keys feed dataset. So this dataset is in the Mosaic library. So first I need to call the library. Wait a sec. I think I mean, oh, sorry. And then I just need to call data keys feed. Okay, good. So by doing this, we already done like the data import. So the next step, I'm going to do the first question. So what's the coefficients of the explanatory variable? So basically, it asks us to build our model. So this is a model construction. And for this one, it's pretty simple. We just need to build a linear model because there are no other requirements. And I believe this question is just to ask for linear model. So what I need is I can call it model and LM, which represents the linear model, linear regression, whatever you want to call it. Um, so what is our predictor? So we want to predict the length of each case and then using their gender. So what we want is we need the length as our y value, which is the output, and also sex as the input data. And data comes from the keys feed. Okay. So now we have our model. So you may want to call the summary function and just put your model in the summary function that will return some statistic about this model. So what you can see here is, so we have some residual statistic and also we have some coefficients. So what we had is, so the intercept is basically the beta zero in our in our model. So which means this will be the interception point if you have, so it is basically the average height or length for each case if you have a zero in your x variable. So what is the x? So in this case, it said like sex is g. So I don't know what the g means. So we need to go back to see what's our data. Okay. So here, in the sex column, you have B, B, B. So basically, I think B means boy, and so the G is represent for girl. So what that means is, if your x variable, if you okay, so if the sex attribute is a girl, then you will need to subtract this amount from your model. And if you if you if the gender is a boy, so which is male, so you don't need to. So the x variable will equal to 0. Okay, so and what's the second? Okay, so the first question, how would you interpret this? So one thing you can do is you can just write down like um, what that means is, so your answer might be, okay, maybe use this. so this is my answer. My answer for this question would be like y hat. So what I may want to use. Okay, so so the hat y, wait, hat y. I don't know why this didn't show. Okay. Okay, so y hat equal to so that's a predicted value. So your y hat will equal to, remember, our intercept point is, so this is our beta 0 plus beta 0 plus beta 1. In this case, it's a negative, so I can directly subtract this. And the product. Okay, so what's a cross product mean? Okay, so maybe we just ignore that product sign, and I can have my x, my x value. So in this case, the x value is just a binary value, so you either have 1 or 0. If it's a girl, you have 1. If it's a boy, you have 0. So my answer for this, so this is our model, and what I can say is, so if my predictor is if the gender is female, then x equal to 1, and we need to subtract 0.78 feet from 25.1050 feet. So basically saying like I can regress all the data, and just say like if I have a girl, then its fit is probably the average of this of her hats will probably fall into this. Oh wait, I don't. Fall into this range. Yeah, I'm not too familiar with the data set, like what is the unit, the measurement of this data set. So I would just say this is a feet, but it might be other units. So okay, so I can just leave it here for now, and I can move to the second question. So the second question is ask us to build a confidence interval, right? Interval for the model, for the coefficient, right? So the question said like we want a 95% confidence interval for the coefficients. So which means if I were to estimate the like how well my coefficients can be for this model, so I need like a 95% confidence that say in this range, I can guarantee 95% that my my result will fall into the right. So the actual value, actual coefficient will fall into this range. Okay. So what we need to do for this one is just, so remember what is a coefficient, a confidence interval for 95%. So the confidence interval for that will be let me give you the answer. So okay, so if you go to this, you can see like this is a confidence interval, 95% confidence interval, and what you need is your beta I, which in this case is just beta 1, because the question is only asked for the explanatory variable, so we don't need to estimate the confidence interval for the intercept point. So we need the estimated value of the coefficients, and also we need the standard error for the coefficients. So what is a standard error? So basically it will say like um, if you remember like in statistics how we calculate the like when we do the calculation for the z value for z score, so you will need the standard error, right? So that's the standard. So that's basically you take the standard deviation divided by the uh, square of the number of data points. So okay, so here I'm just gonna plug in this formula. Maybe I should copy paste this formula just for your reference. Okay, so it doesn't work well. Okay, so okay, I will use like hat the beta hat I. Okay, so minus here is that like 1.96, but that is just the if you look at your normal distribution table, if you look at the normal table, you go to the 97.5 percent. That is the value corresponding value for the 97.5%. Why we use 97.5%? Because this is a two-tail testing. So we need to take the 5% and divide it by 2, and that's 2.5% on each tail. Remember the bell-shaped normal distribution, right? So if we want our data fit into the bell-shaped, we need to take some part from the left tail and take some part from the right tail. So that's why we have the 95%. And standard error of the beta I. Okay, so I can just copy this code, comma, and switch the sign to a plus. Okay, that's our confidence interval, and I can call it CI confidence interval. CI equal to this. Okay, so next, so basically just code it and say so so what I want is my beta. Let me see, what is my beta 1? My beta 1 can come from the summary table, right? Not sure if this is a good way to do it. Let me see. So my beta 1 coefficient. Okay. Let me see what the output. Beta 1. Okay, it's null. So I don't think this looks right. Okay, now we have the coefficients, and in the coefficients, I want the data from the second column and second row. That's the standard arrow. That is a standard arrow for our predictor, right? So I'm going to say I want the data from the second row of the second column. Let me see. What's my beta 1? Okay, and we got this number, 0.407. Okay, so the next, oh wait, sorry, my mistake. So this is supposed to be our beta 1, but I made a mistake. I put the standard arrow into our beta 1. So I actually want the second term from the first column. That should be it. And the standard arrow, SE, equal to, let me put this, second term from the second column. Okay. So I also I can print it out like I see, and I want to also check my beta 1. Okay, all good. So next I just need to write down my confidence interval. So one way you can just write it in the vector, that's what I preferred. But also if you like, you can just say upper bound, lower bound, what's the upper bound and what is a lower bound it is. So I believe there should be a way to name it. Let me try this. So that's beta 1 plus beta 1 plus, okay, let me see. Beta 1 minus, that's a lower bound, right? So beta 1 minus, oh, sorry. I think I should put this. So my lower bound equal to beta 1 minus 1.96, but here for accuracy purpose, so we need to use the code QNOP. That's a percentage. So if I put x equal to a percentage, it will return me the correct value. Okay, so times what? Times standard error. And my upper bound equal to beta 1 plus my Q norm 0.975 times standard error. Okay, just want to make sure we have all this lower and the upper. Okay, so I can print out my CI. So this will be the range, my confidence interval. All right. So next step, okay, so let me just finish the second question. So find out 95%, okay, we found it, and we need to interpret the interval carefully in the context of this situation. So normally when we trying to answer this question, we always say like, so the confidence interval basically tell you, like what is the probability of the actual value lying with your estimate value. So with this confidence interval, I can say like, I can guarantee you that 95% of the chance that the actual estimator will fall into this interval. So there are still a 5% chance that it will go over the lower bound or the upper bound, but 95% is pretty good estimate, like 95% of the time that the actual value will fall into this interval. Okay, so that's and in this context, it's just saying like I can have like 95% of the chance that to tell you a true value. No, not a true value, but I can use this model to predict the height of a girl or a boy with 95% of chance that I can give you the correct answer, because I am confident that my coefficient is actually 95% in this interval. Okay. So, there is another way that you can use this. Actually, I think is Quantel and no, not the other way. Sometimes you can use like 95% of the data. That will also line up like how much a percentage of the data will fall into this your prediction, your predictive value. So what is the actual amount? So anyway, so this will basically just give you an idea like how you to interpret this confidence interval and what that means. Okay, so the next part is number 4. According to this model, is there convincing evidence that boys' feet on average is longer than girls' feet? Okay. So this is hypothesis testing. Hypothesis testing. When you're up to this stage of your of this question, you can pretty much like borrow some result from the prior question. For most cases, you can. And in this one, it's just a slightly difference because the prior question asked for the coefficients, but this one is like I want to compare the, I want to test like if it's true that boys' feet on average is longer, equal, or less than the girls' feet. So that's our is kind of different, but what that means is um, you can translate that if it's true that the girl's age is um, the boy's age is quite it's on average longer than the girl's age, you can just assume that this number, this coefficient is pretty much like it's a negative because when you have girl, your x value equal to 1, then you have on average you need to subtract the coefficient's amount out of the 25 25.1050, right? So that's one way to think about this question. Another way is we normally do is we can test on the mean value of these two population or the sample, right? Because we have girls heights, we have boys heights, and what we can do is we can test the mean value of these two, right? So what I'm gonna do is, so we call that x1 equal to okay, let me just call it mu1. Mu1 is the girl's height because we in our model we call the girl, we default the girl as 1, right? So I'm gonna use the keys feed data, and from the keys feed data, wait, it should automatically populate something for me. Keys feed. Okay, never mind. Maybe I just okay, when this okay, what I want to do is I want to test like if this value okay, wait a minute. So let's go to our data table. So we want the length, right? So we want the length that when my keys feed sex. Oh, I know what's wrong. Okay, I need to put in the coding section. That's why I don't get it. Let me just double check. Okay, now I have this. When this equal to girl, then that's my mu1. And my mu2. Okay, so this test is okay. Test for boys. Okay, maybe it doesn't matter the order, but it's just makes more sense if I put mu1 is a boy's average heights for boys. So next I need the girls' feet. Wait. And I can do the same thing here. That equal to G. Right? That's a girls' feet. Okay. So mu1 and mu2. I'll attempt to apply non-function. Oh, sorry. I need the mean function for this. Okay. I need the mean function. Error. Mean. Probably because I need a bracket instead of round parentheses. Okay, this works. Change to this. Okay, good. So when I'm running my hypothesis testing, I needed to know a couple things. So first, what is the z statistics? So I found this valuable information on Google, and it said like if I have a test of significance for two unknown mean and unknown standard deviation, which is our case because we only have a sample, so we don't know the mean and standard deviation for the population. But because we know the data set is pretty large, right? Remember that if we have more than like, I think it's 27 or 21, I believe it's 27. So if we have more than 27 data points, so we probably so the distribution of this sample will asymptotically equal to the normal distribution, right? So this in this case we can simply assume the normality. Just assume it's a normally distributed. So we can use this formula here, right? I'm not gonna code the formula. You can just look at it, and then we can put it in our R code. Okay. So what I'm gonna do here, so I can call it t equal to, so the top, you use your estimate value minus 2 and divided by square root of s1 squared over n. So in this case, one way you can do so you need to count how many boys and how many girls in this set. So I would say, so n1 for boy, I need to count how many of them. So okay, so I want to use a length function when this equal to boy. So let me see if this can give me the here. Okay, so no. That means we have a 39 boy. Doesn't make sense. We will, oh wait. I believe there are total 39 people. If this equal to boy. Let me just copy the entire line. Okay, let's see. Oh, it's 20. Okay, so this one. Good. And pretty much just need to change the length of that. Okay, so that should tell me. Okay, so into there should be 19. Okay, good. So for now we can just calculate this, and also I want to have my sigma 1. Sorry for that. I just need the SD standard deviation, right? Standard deviation of this. Maybe we should use variances because I want to put a square here. So I will just use variance. G. Okay, 2. Okay, should give me some value. Let's check. 1. Okay, so it looks good. So now just plug in the formula, right? Sigma 1, actually sigma square 1, because this is a variant, so let me just call it variant 1 and variant 2. That makes more sense. Okay, variant 1, variant 2. Variant 1 divided by n1 plus variant 2 divided by n2. Okay, that's my test statistic. Okay, so print it. So that's 1.91. Okay, so with the test statistic, we need to go back to our normal table, right? If you go back to your normal table, you should be able to like see what is the percentage, what is the probability of that. But in here, I believe we can do this. T. Okay. So that's 95%. So that. Give me 1 second. I need to make sure which one is the correct. So basically we want to use this test statistic and just use that to tell us some information, to imply something like what is a p-value, what is a p-value of our test statistic, our model. So let me Google the p-value in RStudio. I believe there is one function that can. Okay, so if you look at this, that's 0.06235, and if you just check this number, 0.0620, it's not exactly the same, but I would say it's pretty close, and maybe I need to the lower tail, probably false. If it's false, let me see. Oh, I don't think that's a problem. So this is an unused argument. Maybe use a p. Okay, false. looks right. Let me see. When we have this, okay. So what I said is, once we have this amount, I can do the absolute negative absolute 1 minus 2. Oh, okay. Okay. P normal mean is this. Standard. It's basically the same thing. Let's say don't use the one minus P norm. One minus P norm is 0. Okay. I guess I just need to double check, like, if this amount, it doesn't look the same as we have it here. Oh, I see. Maybe we didn't run the right testing. Right. So I would say probably we want to use the first testing method. Like we can test for the coefficients. So if you test for the coefficients, right? If you test for the coefficients, you want to make sure that coefficient is not 0, right? If it's 0, then that's wrong. Okay, so I'm going to say so beta 1 minus 0, so which is 0, right? Beta 1 divided by beta 1 divided by the standard arrow. Let me see. Yeah. Theta 1 divided by okay, really just need to refresh and make sure everything I tell is correct. Okay, so we have this, and population coefficient. Population correlation coefficient. Okay. So what I believe is should be this case is we need to use the estimate amount minus that and divided by the estimated coefficient, standard arrow. Okay, so which is the standard arrow? Let me just P norm, so 1 minus P norm. Wait. The that does not 27%. Still looks way off. Even when you multiply by 2, I don't think that's a good risk. So this is our estimation. Estimated value divided by this. Let me just go over some notes. And okay, test the statistics. Sorry. Okay, we were supposed to test. Okay. So I'm gonna show you this tutorial said like if we were doing the t-test, so we want to test if these two were the same. Okay, so because we were doing maybe it's just giving me the same answer. And if I multiply this by 2, they should gather not getting right answer. Right. I'm not so sure if I can refer back to this p-value because it just might be different, I guess. So if you can follow this formula, I'm pretty sure like this could be a good way to do like estimate the average for boys, estimate the average for girls, and see what is the differences. So this is a this one is supposed to be a one-tail test because you either have mu1 greater or equal to mu2 or mu1 less than or equal to mu2. So it's a one-tail testing. But for this one, yeah, it's still one tail. Like your estimated coefficient beta 1 hat is either greater or equal to 0 or less than or equal to 0. But you can also do a two-tail test. Like you can argue that in that case you can argue that my null hypothesis, I want to say like yes, there is no difference between boys and girls, so the coefficient is supposed to be 0, right? Okay, so that's pretty much about it, and thank you for watching, and I hope this will be helpful to you, and leave some comments, and also if you have some answers to my questions, you can also just leave it in the comments. Yeah, thanks for watching, and have a nice day.